Okay, past units have shown us that like using energy is a useful way to solve problems. We've talked about energy for objects that are translating, but there is energy associated with rotation, and it's called rotational kinetic energy. Okay, so we are going to use Ke with a subscript ROT to as the variable for rotational kinetic energy, just to show the difference between just a Ke is going to be translational kinetic energy. And remember, the K that we've defined equals 1/2 mv squared. Okay. When we're looking at rotational kinetic energy, well, kinetic energy is just energy of motion. So let's see if we can use our understanding of rotational kinetic energy to kind of come up with a formula for the rotational kinetic energy. So what we're going to do is we're going to just take like a very simple, probably ineffective fan blade. So this is our fan blade here. Okay. And we're going to split it up into like as many small pieces as we can. So just so that you all can see, these are not very small, but really let's pretend that these are like infinitesimally thin, like little sections of this fan that we're splitting it up into. Okay, so we're gonna just split it up into tiny little sections. Okay, and then some section out here, okay, let's say right here, we are going to call this, we're going to try to determine the rotational kinetic energy of this little piece of the fan right here. Okay, and we're going to say that it's infinitesimally small, so really all parts of that little mass, let's call it Mi. Okay, so a little tiny piece of the fan is gonna be a distance r from this axis of rotation. So let's say it's rotating around this. So we're gonna call this radius of that Mi, that little mass I. Okay, so that little tiny piece is rotating, right? So if we wanted to just use our rotational kinetic, or our regular kinetic energy equation, okay, we would have 1/2 m, whatever that tangential velocity of that object is, squared. Okay, that would give us the kinetic energy. But we know that we want to look at rotational kinetic energy. So that, let's say we just know about how it's rotating. Well, if we know its angular velocity, we actually know, because we know Ri, we know that its tangential velocity is just omega times that Ri. Okay, so let's rewrite this. Let's say that 1/2 m, and let's just put the little subscript I in there. Ri times omega. I flipped them around, sorry, but you can do that. Okay, so we get an equation for the kinetic energy of that one little tiny piece of the fan. Mi Ri squared omega squared. Okay, so that is just a tiny little sliver of the fan. That's its kinetic energy. But we really have a bunch of these masses. Like if we've made it infinitesimally small, there's like kind of an infinite number almost. Well, not infinite, but there is a bunch of little masses all along this fan blade. So to find the rotational kinetic energy, Ke rotational, we would need to add up like all of these little masses. So if we took here and just labeled them M1, M2, all the way down, all the way to the end of this fan, we would need to do KE of 1 plus KE of 2 plus KE of 3, right? And so on. So we're taking this equation here for each of those little masses, those little slivers of the fan, we could add them all up. KE3 and so on, all the way until we get to the last one, KE, let's call that N. Okay, however many number of little segments we had. Okay, but in math we know that when we sum up a bunch of things, you can use summation notation also to show that. So let's use summation notation. So that would mean we're going to sum, whoa, extra little squiggle there, sum from I equals 1 all the way to n, okay, of all of those kinetic energies. Okay, but we know that kinetic energy equation here for each little piece, we wrote that right up here. You can ignore this little diagram. Ignore that for now. We'll come back to it. So that's going to equal the sum of, from 1 to n, of mi ri squared omega squared. And we have a 1/2 in here too, and I'm actually going to write that 1/2 out front because they're all going to have the 1/2. And they're actually all going to have the omega as well. So really the only thing that changes for each little piece is the R. And likely if it's, I mean, it may not be a uniform concentration of plastic or whatever it's made out of. Likely the masses are similar to each other, but they might be slightly different. Okay, so what we get, and let me rewrite this. We get KE rotational equals 1/2. We have this term here, a summation of all those little masses times their radius. Okay, and then they all are going to have the same angular velocity, because the angular velocity is just how far you rotate through, and for every point on that fan blade, it's going to, the theta will be the same. So here's our equation for our rotational kinetic energy, okay? And it looks similar to our KE equals 1/2 mv squared, okay? We have our kind of velocity component. In this case, it's the angular velocity. In this case, it's the tangential velocity. Okay, we have our 1/2, exactly the same. Okay, but then our mass value is what is kind of different here. Okay, so this term right here, we actually have a special name for it. It's kind of like our rotational mass. If you think about it, if you're rotating something further away from its axis of rotation, that's different than if it's very close to the axis of rotation. It like kind of feels heavier the further away it is. Basically we have a rotational mass, or we call it a rotational inertia, is what this term is called. Okay, and it's the mass distribution. So basically it incorporates both the mass and its distribution from the axis. So mass plus its distance from axis of rotation. Okay, you also might see this called the moment of inertia. Okay, I like the term rotational inertia because moment is kind of like a weird word to use because it's not like associated with a moment in time at all. But you may also see that rotational inertia is called the moment of inertia. Okay, so for every object with a different shape, you're gonna have a different value for this rotational inertia. The rotational inertia, we actually give that just to simplify things and make this equation look simpler. We call rotational inertia, you're going to love this, is an I. Okay, so we give it the variable I. Okay, so if we rewrite our kinetic energy, our rotational kinetic energy, we have 1/2 I omega squared. So that I kind of replaces the m in our tangential kinetic energy equation, or linear. I don't know why am I saying tangential? Linear kinetic energy equation. Okay, so for every type of object or distribution of mass in an object, and depending on where the axis of rotation is, you're going to have to calculate, or you could calculate this I value. But fortunately, there's tables and information online about those I values, so those rotational inertias or moment of inertias. So here is just a table of some examples, and on their practice problems you'll be doing, I'll give you a table similar to this where it gives you a formula kind of to figure out what that I value is, depending on both the type of object and its axis of rotation. So you'll notice that these 4 I'm about to circle, these are all thin rods, okay, but they're all being rotated about a different axis. So there's a different formula to determine the rotational inertia. In these formulas, the m just corresponds to the object's mass. Probably could figure this out. And then the r value is whatever's shown in the picture. It's shown in the diagram. Okay, like for this one, we have 2 r values. You also sometimes maybe will have an L, which will also be shown in the diagram. Okay, so you will have to determine this I value. It'll be different kind of every problem, unless you have a similar object that you're analyzing. But let's take a look at an example. Okay, so here we have a practice problem. So we have a reel on a lawnmower rotates as shown at 10 pi radians per second. Okay, so we know our value for omega equals 10 pi radians per second. Okay, it has a mass, so we know our mass value is 3.5 kilograms. Okay, and it has a radius of 4 centimeters. So I'm going to convert that 0.04 meters, and that's our radius r. Okay, we're supposed to find the rotational kinetic energy. So our Ke rotational equals 1/2 I omega squared. Okay, but we need to go find what this actual formula for I is here. Okay, so we know we have a rod that's rotating around kind of its center. So let's go up to our chart. That looks to me like it's going to match with this one. We have an axis of rotation. We have a length, but actually the length is not even in our formula. So we just have I equals mr squared divided by 2. Okay, so our I is going to be 1/2 mr squared divided by 2 times omega squared. Okay, so we get an equation for our rotational kinetic energy equals 1/4 mr squared omega squared. Okay, so let's plug in what we know, and I think we actually know everything we need to solve this problem. So 1/4 the mass is 3.5 kilograms. Actually, I'm going to show the units this time, kilograms. R is 0.04. We need to square it. And then our omega is 10 pi radians per second squared. And our 0.04 was in meters. Forgot I said I was going to show the units. Then I didn't. Okay, so that equals, you do it on your calculator, 1.38. Okay, and the units that we're left with are kilograms meters squared per second squared. And we actually have this radian squared, but radians are weird in that they just, it's really dimensionless, and we kind of just put radians in there to like kind of as a placeholder because we're expecting units and to differentiate it from degrees. But really, like, in the radians kind of disappear. It's weird. I'll make a separate video or show or link to a separate video if you're interested why. It's basically like radians are dimensionless and we just kind of ignore them. But kilogram meter squared per second squared, that is a joule. So 1.38 joules of kinetic energy from that rotation. Okay. Last thing I wanted to talk about in this video is basically that now that we know about rotational kinetic energy, that actually just can be added to our energy equation. Okay, so we have energy initial plus any work done by non-conservative forces equals energy final. So this is now recalling from a few units ago when we talked about energy. But now we just have one more type of mechanical energy or kinetic energy that we can add to our conservation of energy equation. So now we have regular kinetic energy initial, okay, plus kinetic energy rotational initial, plus gravitational potential energy initial, plus, do y'all remember this? Elastic potential energy initial. And remember, most problems don't have all of these types of energy, but this is like just writing it all out. And I might run out of room here. Okay, so we have our mechanical energy, kinetic energy, rotational kinetic energy, gravitational potential energy, elastic potential energy initial, plus any work done by non-conservative forces equals kinetic energy final plus rotational kinetic energy final plus gravitational potential energy final, PE final, plus elastic potential energy final, PE final. Okay, so here we go. I'm not going to do an example with this. You just do it exactly like we were doing with our conservation of energy problems. But there is the full equation now because we have added this type of mechanical energy, the rotational kinetic energy.